guys, and welcome once more to this new video on my YouTube channel, where actually we are going to be solving a question on further curve sketching. The question reads: a real valued function f is defined as f of x equals 2e to the x minus 8 divided by e to the x minus 2. Romans 1, find the domain of f in the form negative infinity a union a positive infinity. Romans 2, evaluate the limit of f of x as x tends to negative infinity, the limit of f of x as x tends to positive infinity, the limit of f of x as x tends to a from below, and the limit of f of x as x tends to a from above. Hence, find the equation of the three asymptotes to the curve y equals f of x. Romans 3, find f prime of x and show that y equals f of x has no turning point. Romans 4, obtain a variation table of f. Romans 5, determine the coordinates of the points where the curve y equals f of x crosses the coordinate axis. Romans 6, sketch the curve y equals f of x. And Romans 7, show that the point of symmetry of the curve y equals f of x is ln 2, 3. Let us then move into the solution actually of this question. So we have our real valued function f, which is defined as f of x equals to exponential of x minus 8 divided by exponential of x minus 2 actually. Yes. So the Romans 1 is asking us to get the domain of f in the form negative infinity a union a positive infinity. So actually we have to get this value of a actually. Yes. By of course giving the domain. So once we are going to have the domain actually, it means we already have the value of a here actually. So writing back first of all our function f of x, which is equal to 2 exponential of x minus 8 divided by exponential of x minus 2. How do we get this the domain of definition of this function actually? Since f of x is a rational function, and we know that for this rational function to exist, the denominator must be actually different from 0 actually. So if we obtain the value of x for which this denominator actually is different from 0 actually, we then obtain the domain of definition of this function f of x actually. Yes. So what are we going to do here? We're first of all going to put the denominator to be equal to 0, that is e exponential of x minus 2 to be equal to 0, which implies actually that exponential of x equals to 2. From there we get the value of x to be equal to ln of 2 actually. So we have calculated the value of x for which this function actually doesn't exist. So how then can we conclude our domain of definition? We can conclude our domain of definition by simply removing this value, which is x equals ln of 2, into our set of all real numbers. We then conclude domain of f. That is, we are going to write our domain where ln of 2 is not included actually in our set of real numbers. So in the real numbers actually ln 2, we have to remove it from there actually, and that gives us actually the domain of definition of this function f of x actually. So from which we conclude that actually the domain of f is equals negative infinity ln of 2 union ln of 2 positive infinity. From here we can clearly conclude that actually the value of a actually is equals to ln 2 here actually. So this is the domain of f actually. So Romans 2 is asking us to evaluate the limit of f of x as x tends to negative infinity, the limit of f of x as x tends to positive infinity, the limit of f of x as x tends to a from below, and the limit of f of x as x tends to a from above. Let's first of all get the limit of f of x as x tends to negative infinity. So writing it the same as writing the limit of f of x, that is where f of x equals to 2 exponential of x minus 8 divided by exponential of x minus 2 as x tends to negative infinity. So replacing everywhere we see x with negative infinity, we are going to get 2 exponential negative infinity minus 8 divided by exponential of negative infinity minus 2. Now exponential of negative infinity tends to 0 actually. So in the numerator we are going to obtain 2 times 0 minus 8, which gives us negative 8 in the numerator, and the denominator we are going to obtain 0 minus 2, which gives us negative 2 actually in the denominator. So we are going to have negative 8, which is the numerator, divided by negative 2, which is in the denominator. We get actually our limit to be equal to 4. That is the limit of f of x as x tends to negative infinity to be equal to 4. Let us then get the limit of f of x as x tends to positive infinity. The limit of f of x as x tends to positive infinity is simply the limit of 2 exponential of x minus 8 divided by exponential of x minus 2 as x tends to positive infinity. So replacing everywhere we see x with positive infinity, we get 2 exponential positive infinity minus 8 divided by exponential positive infinity minus 2 actually. So in the numerator we are going to obtain what? 2 exponential of positive infinity gives us positive infinity. Positive infinity times 2 give us positive infinity. And if a bigger number, that's infinity minus 8, will still give us infinity actually. So in the numerator we are going to obtain infinity. And the denominator, what are we going to obtain? We are going to obtain exponential of positive infinity with this of positive infinity. And positive infinity minus 2 is still positive infinity, because taking a large number, very large number, subtracting 2 from it will still remain. Actually, that will not change any big thing. So in the denominator we are still going to have positive infinity. So therefore we get positive infinity divided by infinity, positive infinity divided by positive infinity actually, which is actually an undeterminate form actually. So we have to remove this undetermination actually. How do we do it? We can use the L'Hopital's rules actually. So from L'Hopital rule, which says that what, in order for us to get this limit actually, we are going to differentiate actually, okay, the numerator, okay, separately, and differentiate the denominator actually separately. At the end we get actually the limit of that result which we obtain. That is the limit of f of x, the limit of f of x as x on positive infinity, that is the limit of 2 exponential x minus 8 divided by exponential of x minus 2 as x on to positive infinity is still the same as the limit of 2 exponential x divided by exponential of x as x tends to positive infinity. What have we done here actually? We have simply differentiated the numerator separately. That is, if we differentiate this numerator actually, we are going to obtain 2 exponential of x, and if we differentiate also the denominator separately, we are going to obtain exponential of x. We calculate that this exponential of x are going to cancel each other. Actually we are going to be left with 2 actually to be the limit of f of x as x tends to positive infinity. Let us now get the limit of f of x as x tends to a from below. We know that a is ln of 2 actually. So the limit of f of x as x tends to ln 2 from below actually will be the limit of 2 exponential of x minus 8 divided by exponential of x minus 2, okay, as x tends to ln of 2 from below. Actually, how are we going to proceed here actually? To do this, we first of all need to know the value of ln 2. Ln 2 actually is 0.693 actually. Yes, I'm going to make that actually. Yes. So once we say that, if we want to calculate the limit of f of x as x tends to ln of 2 from below, okay, we are going to take from that 0.693, we are going to take 0.3 actually. So we are going to take a number which is quite less than, very less, that's the smallest number in the 0.693. In this case, if we take 0.6, okay, and substitute it everywhere we see x, we substitute with 0.6 actually, we are going to obtain that this limit actually is going to move towards positive infinity. That the behavior of this limit is going to move towards positive infinity if we continue on that path, that is substituting everywhere we see x with 0.6, we are going to obtain that. But on the other hand, to get the limit of f of x as x tends to ln 2 from below, that is the limit of 2 exponential of x minus 8 divided by exponential of x minus 2 as x tends to ln of 2 from above, what are we going to take here? We are going to take actually a value which is quite the greatest value, okay, in the largest value, okay, in 0.693 actually. What then is that number? We can take, for example, we can round up that if we take 0.7 and substitute it here actually, we are going to obtain, everywhere we see x here actually we replace with 0.7. Once we are going to do that, we are going to realize that this limit actually is going to turn towards negative infinity. So we can therefore conclude that the limit of f of x as x tends to ln of 2 from above is equals to negative infinity. Actually we can conclude therefore our asymptote from here actually properly. Why? Because we have clearly see that since the limit of f of x as x tends to negative infinity give us a finite number, that is 4. The limit of f of x as x tends to positive infinity give us also a finite number which is 2 actually. We can therefore conclude that 4 and 2 are our horizontal asymptotes actually. Yes. And similarly, since the limit, okay, of f of x as x tends to ln of 2 from below give us positive infinity, that's an infinity number, an infinite number, okay, and the limit of f of x as x tends to ln of 2 from below give us also an infinite number. We can therefore conclude that ln of 2 actually is our vertical asymptote actually. Yes. So concluding that is y equals 4 and y equals 2 are the horizontal asymptotes and x equals ln 2 is the vertical asymptote, which answered therefore the Romans 2 of our question actually. Yes, so actually the Roman 3, you are being asked to find f prime of x and show that y equals f of x has no turning point actually. So let us first of all get f prime of x. We know that our function f of x is actually equals to exponential of x minus 8 divided by exponential of x minus 2. So in order for us to differentiate this, actually we use the quotient rule actually. Yes, so f prime of x will simply be equals to what? vu prime minus ub prime divided by v squared, where v is actually what's in the denominator and u is actually what's in the numerator. So saying that is vu prime, v which is what actually is in the denominator, u prime is simply the derivative of the numerator. That if you differentiate the numerator, we are going to obtain 2 exponential of x minus u which is the numerator, that is 2 exponential of x minus 8. v prime is actually differentiating the denominator, we get exponential of x divided by v squared, v which is exponential of x minus 2, that is we square it actually. This is actually the quotient rule actually. Yes, so we can clearly factorize, we can clearly see that exponential of x is common here, exponential of x is common in the numerator actually, so we can factorize exponential of x in the numerator. We obtain f of x to be equals to exponential of x open big bracket 2 exponential of x minus 4 minus 2 exponential of x minus 8, close our bracket, close the big bracket, divided by exponential of x minus 2, all that squared. We can clearly see that 2 exponential of x is going to cancel with these 2 exponential of x, that is 2 exponential of x minus 2 exponential of x gives us 0, and the negative 4 minus 8 gives us 4 actually. So in the numerator we are going to obtain 4 exponential of x actually divided by this exponential of x minus 2, all squared. So we get f prime of x to be equal to 4 exponential of x divided by exponential of x minus 2, all that square actually. So we know that at turning point, so this is actually the first part of the equation, which is the derivative, that is f prime of x, which is actually 4 exponential of x divided by e to the x minus 2, all that square. Let us then show that y equals f of x has no turning point. We know that at turning point f prime of x equals 0, which implies that what this f prime of x actually, which is equals to 4 exponential of x divided by exponential of x minus 2, all that square, is equal to 0. Simplifying it, we are going to get 4 exponential of x to be equal to 0, and we can clearly see that x has no real solution. Why? Because there is no value of x for which this left hand side is going to be equal to 0. You can never get a value because exponential of x is always positive. It can never be 0, this exponential of x, no matter the value of x you take. Yes, so this actually can never give you 0, reason why it has no real solution. From here we can therefore conclude that f of x has no turning point actually. So actually in the Romans 4 we are asked to obtain a variation table of f. So to do obtain a variation, we first of all need the domain of definition, actually f prime of x and f of x. So we need to determine the sign of f prime of x in each of the intervals. That we need to determine the sign of f prime of x in the interval negative infinity ln of 2, and the sign of f prime of x in the interval ln of 2 positive infinity. So determine the sign of f prime of x in the interval negative infinity ln of 2, we are going to obtain f prime of x be positive in this interval. That is, if you take any value in the interval negative infinity, in between negative infinity and ln of 2, we are going to obtain the sign of f prime of x to be positive. Similarly, in the interval ln of 2 positive infinity, if you take a number in between here, we are going to obtain the sign of f prime of x to be positive. Since the sign of f prime of x is positive in the interval negative infinity ln of 2, we are going to actually see that our function f of x is going to be increasing in the interval negative infinity ln of 2. And we know that the limit of f of x as x tends to negative infinity is actually 4, and the limit of f of x as x tends to ln of 2 from below is positive infinity. Similarly, since the sign of f prime of x in the interval ln of 2 positive infinity is positive, it implies our function f of x is going to be increasing in the interval ln of 2 positive infinity. Yes, actually. And we calculated the limit of f of x as x tends to ln of 2 from above to be negative infinity, and the limit of f of x as x tends to positive infinity to be 2 actually. So this is actually our table of variation, that is the variation table of f actually. The Roman solver have to determine the coordinates of the point where the curve y equals f of x crosses the coordinate axis. So here we are simply going to obtain the intercept. So what happens when x equals 0? When x equals 0, we are going to obtain y to be equal to 2 exponential of 0 minus 8 divided by exponential of 0 minus 2, and which gives us 6, because exponential of 0 is 1. 2 times 1 gives us 2, and 2 minus 8 gives us negative 6. And the denominator, we are going to have 1 minus 2, which gives us negative 1 in the denominator, from which we get therefore y to be equal to negative 8 to be negative 8 divided by negative 1, which gives us 6 actually. We therefore obtain the point 0.6 as the first intercept actually. And what happens when y equals 0? When y equals 0, we are going to obtain 2 exponential of x minus 8 divided by exponential of x minus 2 to be equal to 0. For which we have 2 exponential of x minus 8 to be equal to 0, where we therefore conclude that x equals ln of 4 actually. From which we then obtain the point ln of 2, 0 actually. Yes, so the Romans 5, let me ask to sketch the curve y equals f of x actually. Yes, so to sketch this curve actually, we need some parameters, okay, in order for us to sketch this curve actually. So in sketching actually, okay, curves, we need something which is very important. That is, we need the variation table. Is very, very important actually. Yes, we need the intercept actually. We need the turning point if there are turning points, but in this case we clearly calculated that, we proved that there are no turning points actually. Yes, so once you have those parameters, of course, with the asymptotes, their insights, we can clearly therefore sketch our curve y equals f of x actually. Yes, so representing our xy plane, first of all, remember I obtained these values of x and y depending on what I had, okay, depending on my values which I obtained actually. Yes, so in the first place I had first of all my asymptotes actually. So we have the horizontal and the vertical. We have the 2 horizontal asymptotes and the 1 vertical asymptote. That is, y equals 4 and y equals 2 are the horizontal asymptotes, and x equals ln 2 is actually our vertical asymptote. It's our vertical asymptote actually. We have to represent also the intercept. We obtain the intercept 0, 6 actually, and the intercept ln 4, 0 actually. So representing them, we are going to unwrap those black dots. We are going to represent our intercept actually. Yes, so since we have no turning point, we cannot represent it here actually, but if we had a turning point, we would have represented it there actually. Yes, so I take it back. I represented my x and y axis. I represented my asymptotes, okay. I have represented my intercept actually, and since there are no turning points, I will not represent it here actually. Then how then can we come out with a graph? Simply we then use the variation table here in order to come out actually with our sketch actually. Yes, so representing our variation table which I had previously explained today, yes, we are going to obtain this. We can clearly see that what is the behavior, how are you going to actually sketch graphs here actually. We are seeing here that what these at this level here, we can clearly see that in the interval negative infinity ln of 2, okay, we have f of x which is increasing, that is moving from 4 to positive infinity actually. So we can represent it here, and if you see it closer, we touch actually this intercept actually. Yes, so representing that, we are going to obtain this actually, that is from 4 to positive infinity. That is 4, which is our horizontal asymptote, 4 moving towards positive infinity, and does not touch this asymptote actually. Yes, and of course similarly in the interval in 2 positive infinity, okay, we have the curve, you have the curve moving, you have the graph moving from negative infinity to 2 actually. Yes, so from negative infinity to 2, that is, it comes like this, it touches this intercept and it moves to 2 actually here. So representing it, we are going to obtain this actually. So this actually the sketch, okay, of the curve y equals f of x actually. Yes, so the Roman 7, we are being asked to show that the point of symmetry of the curve y equals f of x is ln 2, 3. How do we show it actually? Since there are 2 horizontal asymptotes here and there is 1 vertical asymptote actually, we are simply going to look for the midpoint, okay, between these 2 horizontal asymptotes, okay. That is going to be the value of y actually, and the value of x is simply this vertical asymptote which is alone, that is x equals ln 2. But if we had 2 vertical asymptotes, which is not our case here, we will have this we will have actually added the 2 and divided by 2 actually. Yes. So the x coordinates of our point of symmetry is simply going to be equal to ln 2, which is our vertical asymptote, that is this point here is actually going to be equal to ln 2, and the y coordinate is going to be 4 plus 2 divided by 2. By simply getting the midpoint between these two horizontal asymptotes, we get our y to be equal to 3 actually. We can therefore implies that the point of symmetry is actually ln 2 3, which actually what was required for us to prove actually. Yes. So generally if AB is a point of symmetry of a curve, then f of a plus x plus f of a minus x equals to 2b. So if we prove this statement, you can also get the result perfectly. That you substitute a actually by ln 2 and b, which is 3, and you therefore prove that the left hand side equals to the right hand side. It is also another methodology actually. So thank you very much for watching this video, and remain tuned for a very next interesting mathematics further mathematics question. Thank you very much.